In the previous lecture, we discussed the quantization of electron orbitals, how the orbitals are quantized in the K space and how they are quantized in the real space, and how these orbitals are related to the magnetic field and the carrier concentration, flux quantization, and we also introduced the concept of Landau levels and also Landau tubes in the 3-dimension. So in this lecture, we will look into the density of states, filling factor, and interesting transport phenomena, that is the Shubnikov-de-Haas effect and Shubnikov-de-Haas oscillation, which is an associated phenomena of quantum Hall effect, and the concept of magnetic length. So the first question that one would like to ask is, how many states are there in each Landau level? These Landau levels are defined in the K space. So how many states are possible in the Landau level? Okay. Now, the cartoon here shows the distribution of the states in the absence of any field and the formation of Landau levels, which are represented by these Laurentian shaped functions there. Okay. And with the energy quantized n plus 1 by 2 h bar omega. So starting with 1 by 2 h bar omega, 1 plus 1 by 2, 3 by 2, 5 by 2, and so on. Okay. And you can see that the energy spread or energy coverage for each Landau level is whatever this coverage for each of these Landau level is h bar omega c. Okay. So the number of states in an area S per unit energy, okay, is basically the density of states. That is the number of, that is per unit energy per unit area. This is the 2-dimensional case. In 3-dimensional will be unit volume. And this condition is taken B is equal to 0, because that is pretty much fine, because the number of states are not going to change. Okay, the number of states are the number of states in the constituent solid, which is basically the number of states with the constant atoms. So you cannot, the magnetic field cannot change in this situation, the number of states. It's not going to create any new states. Okay. And all the available states are there until this Fermi level here. Okay. So that means the 2-dimensional density of states into the area S. Okay. And you have to multiply by the spin degeneracy 1 by 2, sorry, 2. And that is going to give you the number of states in an area S per unit energy. And you can use this omega c is EB by m, and the number of states in one Landau level, okay, within an area S. Okay. Now you have to be a little bit careful here. Landau level refers to the energy, or it's a orbital, or it is a collection of states in the K space, but that can be scattered many places in the real space. Okay, so don't confuse the Landau level and the actual electron orbital. Okay, electron orbits in the real space, but Landau level is in the K space. Okay, that concept that you have to be a little bit careful. It's a subtle point here. Now, the number of states in one Landau in an area S. So, this is your spin degeneracy, density of states, area S, the same thing here, plus the available energy window of one Landau level, that is h bar omega c. That is what we discussed here. So, when you work it out, you will get Gs into, you can replace the omega c with Eb by m, then you will get a magnetic field term here. So eventually what you are going to get is Gs into E by H into phi. So this E by H is an interesting quantity. It is the magnetic flux quantum. That is what is E by H. So H by E. Okay, that is what H by E. So we can rewrite this thing here as Gs into Gs is spin degeneracy, and B into S is going to give you the phi term, the total flux, and phi 0 is the H by E term, that is the condensed unit of magnetic flux. So now in this case the spin degeneracy is also involved. Okay, so number of spin degenerate state in an area S in each Landau level. This is for one Landau level. Okay, and you are seeing that that is same in all the Landau. It doesn't have any reference to the Landau level here. Okay, all this says is in an area S in each Landau level is equal to number of flux quantum enclosed in that area. But now you know that flux quantum enclosed between every Landau level should be same because the area between every Landau level is same, that we have seen in the previous class. All right. So the take-home message here is the number of spin degenerate states in an area in each Landau level is equal to the number of flux quantum enclosed in that area. Okay. Now there is another concept or terminology called filling factor. The filling factor says how many Landau levels are actually filled at certain field for a given electron density. So the density of states in one Landau level with an energy window Eb by m is given by density of states per unit area into the energy window. Energy window is h bar omega c. And you can replace omega c with Eb by m, then you will get this number 2 Eb by h bar. Okay, and this 2 here stands for the spin degeneracy. Okay, now in this case we have assumed that the Zeeman splitting is not appreciable, so we multiply it by 2. But if the field is very high, you don't need to consider this 2. Then the spin splitting of the Landau levels also one need to consider. So for a given electron density Ns, the number of Landau levels occupied is given by the electron density Ns divided by the number of states in each Landau level at a given B field. And this quantity is called filling factor, generally represented by the letter nu. For example, if you have the B field 2 Tesla with an Ns 5 times 10 to the power 11 per centimeter square, then when you work out this number, what you will get is 5.2. What that means is there are 5 Landau levels fully occupied and the 6th Landau level is partially occupied. That's what it means. Okay. So we can also say that the filling factor is inversely proportional magnetic field. This is also easy to see because when you increase the field, the Landau level area will increase I mean, the number of states in that Landau level also will increase. What that means, filling factor will decrease. So when you increase the B field, the Landau levels will expand, making more and more states inside each Landau level. Okay. So for a constant charge concentration NS, the states in each Landau will increase and the filling factor will decrease. Okay. Now let us inspect this situation a little bit more detail. What is the charge or what is electron dynamics that one would observe when you increase the B field? So here, these cartoons show the density of states or how the states are distributed when you change the magnetic field. So when there is no B field, when B equals 0, there are no Landau levels, it's a continuum distribution, and EF is the Fermi level, which I have noted by the dashed circle. And I'm also assuming that this is a non-zero temperature, though it's a low temperature, but still there is a small width. So that is why I put this Fermi level in this small but thin but broader region. Okay. Now when you increase the B field, suddenly these states will condense onto circles. Those are the Landau levels. Okay. But now the number of Landau levels below the Fermi level is defined by the B field. Fermi level is not going to change. That is defined by the total number of electrons in the system and the expression we have derived in one of the initial lectures. So this dotted circle, that is the Fermi level or the Fermi sphere in 3D, that is going to remain same. That will be the same. That's not going to change. But what is going to happen is the area of this Landau level, that is proportional to B field, B. That is going to expand, each of them. They'll expand isotropically, but the Fermi level is going to be there. It's not going to change. So what's going to happen is they'll expand, and they will escape or pass through the Fermi surface one by one. So now this is going to create some very interesting situation. I have kind of put the same picture here. So you have B is equal to 0, the continuum distribution, and the moment B is not equal to 0, you have these Landau levels. Each of these are actually Landau levels. Okay, starting outermost, then going inwards. Okay. Now, the spacing between the Landau level and the circumference and the radius of this Landau level or these circles is proportional to B, as given by this equation. Okay. Now, what's going to happen is, it's not the radius, but you have to understand it is the area. Okay, area is proportional to B. So the number of Landau levels below the Fermi level, that is this line here, this is the Fermi level, that depends on the B field. So as you increase the B field, these will expand and they will escape the Fermi level one by one. Now this is outside, this is going out. So you started with 3 states here, right? In this case, you have 3 states and 2.5 states and then 2 states. So as you increase the B field, as we discussed in the previous slide, the filling factor will change, will reduce, and the number of Landau levels also will reduce. But now, but the circumference and the area of each Landau level will increase as we increase the B field. So whatever the states that has been lost below the Fermi level, because the Landau level has passed through the Fermi level as a result of increasing the B field. But equal number of states will be made available below the Fermi level because of the presence of the expanded Landau levels. So what that means is number of states are not going to change. Number of states will be there, but the moment the Landau level pass through the Fermi level, as shown here, the electrons in that Landau level, in that particular Landau level, need to jump back because above the Fermi level they cannot exist. So the moment this goes through here, all the electrons which were here now will go back here. It will jump back here the moment it's passed through. It actually can go back here because now there are more states in this case compared to this state, because this area of this Landau level is now more. So the area is this area is actually increasing as we increase the B field. So there are more states or more space for the electrons to jump back from here to here. So this action of the electron suddenly, transitioning from a higher Landau level to a lower Landau level, the moment it passed through the Fermi surface, is going to reflect in all the physical properties of the system. And this is going to give you oscillative behavior in various physical properties. And the oscillations in magnetic field is referred as de-Haas Van Alphen effect. That is widely used for mapping the Fermi level. Okay, that is something which we are not going to discuss. But the oscillation in the resistance or resistivity is called Shubnikov-de-Haas effect, that we will discuss now. Okay. So in nutshell, what we have discussed now is, when you ram the B field, the Landau levels will expand, the Fermi level of course will remain there. Then when the Landau level pass through the Fermi level as a result of increasing the B field, all those electrons in that particular Landau level will jump back to the one below. Okay, but remember, the Landau level below the Fermi level is also now expanded and got enough space to have those electrons sit there. Okay, so that is the take-home message now. All right. Now let us briefly look at the Shubnikov-de-Haas oscillation, Shubnikov-de-Haas effect. This is nothing but oscillations in the resistivity or conductivity of the material as a function of B field, discovered by de-Haas and Shubnikov in 1930. They observed in the ultra-pure bismuth single crystals. And these oscillations you can see even in this landmark Nobel Prize winning experiment conducted by Klaus von Klitzing. So here there are many curves in this graph. If you look at this red colored curve, you can see that he calls as resistance at B is equal to whatever this high field, 19.8 Tesla. And other resistance is called, he calls Hall resistance. So we are not referring to the Hall resistance, we are referring to the resistance of B field. That is actually the resistance along the direction we generally call RXX. It's along the direction of applied B field. That is the linear resistance or RXX. Okay. Now that is what is plotted here as the red curve, and you can see all those red curves has an oscillative behavior, and it actually goes to pretty low value in resistance. Okay, and that is what we call the Shubnikov-de-Haas oscillation. This is for the silicon MOSFET as a function of gate voltage, and this is for a gallium arsenide device where you can see this curve. There are oscillations like this here also. Okay, that is the Rxx part, which is nothing but Vxx divided by the current through it. So what you're seeing is an oscillation in the Vxx, which is an oscillation in the Rxx. And the red curve is the Rxy, that is a Hall or transverse component of the resistance, which we will discuss in the next class. Okay, and this is in a gallium arsenide, aluminum gallium arsenide 2-dimensional electron gas sample. Now we know that the filling fraction nu is periodic in 1 by b. Okay, ns 2e by h into 1 by b is actually periodic in 1 by b. Okay, so this is again how the Landau levels are going to behave when you increase the Biff field. So you have no Landau levels, a continuum state, then you have 3 Landau levels, 2.5-ish, because this is about to go out of the Fermi level, and then 2, after this is left, this 2, and so on. Then finally you will get 1, okay, and so on, like that. So now let us look at the concept of resistance. Philosophically, what it means is it is the impedance or the opposition offered to the forward propagation of the electrons. That is what is resistance. What that means is resistance means there is a component or there is a momentum component which makes electron scatter back. So it's a backscattering component. When you say backscattering or scattering, it actually needs states for that purpose. Now you will see very soon in the next class that these Landau levels are actually, these Landau levels correspond to states which propagate only in one direction. The action of applying a magnetic field is going to basically remove the time reversal, and you cannot have the electron coming back. That you will see in a minute, because you have to define a few more concepts to reach that point. But just to understand this oscillating behavior, if you don't have states at the Fermi level, you cannot backscatter. In this case, you have states at the Fermi level. There's a continuum state. You can actually backscatter and you will get a resistance. But here, the states are condensed onto these Landau levels, and this Landau level is outside. So these states are not accessible. This Landau level is full. So there are no states available for backscatter because those are already full. What that means is there are no states to backscatter. That means the resistance Rx's component will be 0. But here, when the Landau level pass through, then these there are states. So of course, given the broadening of the temperature, that is why you get broadening of all these Landau levels. That is basically caused by the broadening of temperature mostly. So then you have states here. Okay. Now again, no states, no resistance. Here you have states for the electrons to backscatter, then you have resistance. So all these dips of negligible resistance, actually it should be 0. But when you measure it, it actually is going to be the noise level or noise floor of the instrument, the preamplifier that you are using to measure. Okay. So whenever there are states, you will measure resistance. That is where you are going to get. That is when you are going to get these peaks. Okay. And this splitting is because of the spin splitting. Okay. Now, whenever you have no states, that means in this configuration or in this configuration, here or here, there are no states at the Fermi level to backscatter, so no resistance. That's what is happening here also. Okay. And this is for a graphene sample. The reference is here. when you measure the resistance, the linear resistance or Rxx, that is, if you pump current from here to here, and you are measuring the resistance between any two probes in the direction of propagation of the current, then you will measure this black curve here, which has an oscillative behavior. Okay, so these oscillations are called Shubnikov-de-Haas oscillations. Now, let us look into the Shubnikov-de-Haas oscillations a little bit more in detail, and you will realize that this is highly important technically and for material characterization. So we have the filling factor given by this formula for a given electron density Ns and a given B field, that is the number of Landau levels occupied. And now I have snapshots of the Landau levels for two different B fields, B1 and B2, okay, where B1 is less than B2. And this corresponds to a filling factor nu1, where you have 3 Landau levels below the Fermi level, and this corresponds to filling factor nu2, where you have 2 Landau levels below the Fermi level. Fermi level is marked here. Okay. Now, so as we know, these points correspond to points of resistance or points of no resistance or negligible resistance. That is basically the dips in this Rxx or Vxx oscillation. Okay. Now, from this filling factor equation, this refers to situations where the filling factor differed by 1. So that means Ns by 2 EB1, that will have higher filling factor 3. This will be higher filling factor 2. As per this picture, the difference will be 1. So from that, you can rearrange the terms and get a condition for the carrier concentration N. N is something which is constant, which we are not varying. We will get, that is 2E by H divided by delta of 1 by B. Okay. So by looking at the dips in this oscillation, you can calculate the carrier concentration directly using this formula. Ns is 2E by H delta of 1 by B. Okay. And these oscillations, when you plot in 1 by B, it will be periodic. This is not periodic because this is plotted versus B, the magnetic field. If you plot in 1 by B, then these oscillations will be periodic. So Shubnikov-de-Haas effect, or in short, people also call it SDH effect. SDH oscillation is widely used for the determination of carrier concentration in two-dimensional systems. Okay. Now, let us close today's lecture by briefly mentioning another concept, that is the magnetic length and its connection to the cyclotron radius. So we know the area of the state delta S is H by EB or phi 0 by B in real space. Okay. This we have done before. Okay. Now, the classical cyclotron radius is given by the momentum H bar K is E into R cross B. Okay. Force is E into V cross B. So momentum is E into R cross B. From that, we can get the cyclotron radius RC is MVN, that is the momentum. This is the classical term, okay, divided by EB. And if you equate this to the energy, quantum mechanical energy, you can make a connection between these two. Okay, where omega is EB by M. So you can rearrange it, and what you will get is RC is square root of 2n plus 1 h bar by EB. Okay, that's the radius, cyclotron radius, which is 2n plus 1 into LB, where LB is h bar by EB is defined the magnetic length. So magnetic length is something where the spread of that electron, the physical dimension, where the spread of each state in real space. Okay, the physical dimension of the spread of each state. Okay, so we know that each state is represented by something like this, where that refers to the cyclotron motion of the electron. And of course, the spread will, in real space, okay, this spread will be inversely proportional to B, okay, and in K space, it'll be more, because you can say that when the field is low, it's a larger radius. When the field is less, radius will start reducing. And this density of these states has been also visualized by tunneling spectroscopy techniques, by landmark experiment. And what they have seen is they have seen the spread or the density of states using the tunneling experiment. They measured for various Landau levels. This for lowest Landau level, then you can see the next one, you can see that is larger. The next one, there are 3 Landau levels now, 0, 1 and 2. So you can see 1, 2, 3, there are 3 of them, the largest one here. Then the next one is even larger. Okay. So this has been measured experimentally also, this spread of these Landau levels. This is the mapping of the density of states by tunneling experiment. Okay, and as you can also see here, there are no overlap between different Landau levels, because these are energy eigenstates for the Hamiltonian, which are orthogonal. So they don't cross each other, there is no overlap. So that's what you're seeing here also. You have all the 4 states are here, but there is no overlap between the 4 states. That also you can see. These are orthogonal states that you know from the physics side, but that is also what is seen when these states are probed by tunneling microscopy technique. So far what we have seen is the number of states, the filling factor, the magnetic length, and the oscillations in physical properties of the material as a function of B field. That is what we looked into in this lecture. And the next lecture, we will address the transport characteristics directly. That is the quantum Hall effect, and we also will revisit the Shubnikov-de-Haas oscillations too.